What a sad, sad parabola. Okay, now that that just looks like a fish. Anyway, that is actually a good place to start. Identifying the type of graph that we're given. In this case, we are given a negative, as in concave down, parabola. Right? Or in calculus, we can call it a quadratic. We can think of the function. So that's our starting point. That's what we're given. A negative quadratic. Now the question, very common calculus question, we're asked to sketch the gradient function of that graph. So, just from the analytical side of calculus, we know that if we differentiate, let's say, negative x squared, the derivative will be, in this case, negative 2x. It will be a negative straight line. So a negative quadratic, we expect a negative linear graph. So if we go to our grid, can we draw just any negative line? No. Absolutely not. That's a good place to start. If you have to guess, sure. But we need to identify some key points on that line. So let's have a look at the function and consider the gradient of this function. So the most obvious point to start with is any turning points. So what is the gradient of a turning point? Gradient of a turning point. So I'll use m. The gradient is 0. Right? In fact, they are called stationary points. Stationary points. Or a stationary point in this case. Gradient 0. Now to the left of that point, how would you describe this gradient? Right, it's positive. Right? Positive gradient. So the gradient is positive or it's greater than 0. We call that increasing. And on the other side, right, negative gradient. So gradient's less than 0. We call that decreasing. So there's sort of 3 distinct parts to the gradient of a quadratic. Right? In this case, since it's a negative quadratic, it's increasing first, then it's stationary, then it's decreasing. So, how does that translate to our sketch of the derivative? So a key point, that red point, which is at approximately halfway, maybe like negative half, if each square is 1. On our gradient function, the y value is the gradient. So at negative half, the y value should be 0, because the y value tells us what the gradient is. So once more, this point at negative half tells me the original function has a gradient of 0, which it does, right? That's the turning point. Now everything to the left of the turning point, the gradient is positive. So on our gradient function, the y value should be positive. It should be in that half. So we can draw our line something like so. The steepness of the line doesn't matter too much, for a sketch at least. Right? Now everything to the right of the turning point, the gradient is negative. So again, on our graph, that should be below the x-axis. So positive gradient, 0 gradient, negative gradient. Now for this line, if you just look at this line with no context, it has a constant gradient, right? Itself, it's a negative gradient. But remember, this line is telling us about the original function's gradient. not its own gradient. It's telling us about the original function. Cool. Another little tip while we're here is if you have any turning points, just draw a dashed line all the way down, because usually, not always, but usually they give you the same scale grid, and at those turning points you know you can put a point on the x-axis because the gradient of the original function is 0. Alright, and that would be an achieved question, as long as you had the x-intercept in the right position and it was a negative straight line.